Okie dokie. Let's finish up this section talking about the fundamental theorem of algebra. And what it says, along with its corollary, is that rather than looking at the degree of a polynomial to tell us at most how many solutions there are, the fundamental theorem, along with its corollary, tell us that there are exactly that many. So in a polynomial of nth degree, there are exactly n solutions, or n zeros. Now, some of these zeros could be complex numbers or numbers on the imaginary plane. And remember, those are of the nature a plus bi. And they always come in pairs, conjugate pairs, a minus bi. So when we're looking for all the solutions of a polynomial, like the example on the left-hand side here, when we're looking for all of those solutions, we have to allow for the fact that there may or may not be a complex pair. So let's go look for some in this polynomial. First, I want to use Descartes' rule of signs to determine whether there are any possible complex solutions. So I'm going to count sign changes throughout the polynomial, making sure that it's all there. So I have x to the fourth to x cubed. There's no sign change because there's a positive out front. There's a sign change from x cubed to x squared term, another sign change from the squared term to the linear term, and another sign change from the linear term to the constant. So this gives me three possible positive solutions. So that means I have three, using the rule, I could have three positive solutions or three positive zeros, or less than that by some even number. So 3, the only even number less than 3 is 2. So I could have 3 or 1 positive zeros. Now I'm going to use the same rule, only this time I'm going to substitute negative x and rewrite my polynomial. So if I put a negative x into x fourth, the sign stays exactly the same. A negative x in for x cubed, the sign is going to change. For x squared, the sign stays exactly the same. For x to the first power, I get a sign change. It's not an n, that's an x. And then no effect on the constant. So now let's count our sign changes again. From plus to minus, that's 1. From minus to minus, no sign change. Minus to minus, no sign change. And minus to minus, no sign change. That means no matter what, I'm only going to get one negative 0. Okay? Now, the fundamental theorem of algebra tells me I'm going to have exactly 4 no matter what. So my total has to be 4. So how many complex would I have? Well, if I have 3 positive solutions and 1 negative, then I wouldn't have any complex solutions because 3 plus 1 already equals 4. If I have 1 positive and 1 negative, then I would have to have 2 complex in order to equal 4. And that makes sense because remember, complex numbers, complex zeros come in pairs. So it is possible I'll end up with complex numbers. It's possible I won't, but let's go have a look and see what I actually end up having. Next thing I want to do is come up with some choices for synthetic division to reduce this polynomial into linear factors. So my first, or my leading coefficient, has factors of plus and minus 1. We like that. When the leading coefficient has factors of plus and minus 1, that means we're not going to have any fractions to try to figure out with synthetic division. But my constant term has a lot of factors. So let's go and see what they all are. I have 1 times 120, 2 times 60, 3 times 40, 4 times, 60 divided by 2 is 30, 5 times 24, 6 times, and this gets easier because 3 times 2 is 6, so just divide 40 by 2. 7 doesn't divide by 7. 8 times, again, if 4 times 2 is 8, then 30 divided by 2 is 15. 9 times doesn't divide by 9. 10 times 12, and then the next factor I would be able to put on the left-hand side is 12, but that's just going to give me the pairs all the way back up the other side. So at this point, I'm looking at my list of possible real roots or real zeros is plus or minus 1, plus or minus 2, plus or minus 3. I'm going to say them all. Plus or minus 4, plus or minus 5, plus or minus 6, oops, plus or minus 8, plus or minus 10, plus or minus 12, plus or minus 15, plus or minus 20, plus or minus 24, plus or minus 30, plus or minus 40, plus or minus 60, and finally plus or minus 120. I didn't even want to write all those down. I certainly don't want to try them all in synthetic division, so I'm going to use one of my tools to reduce the number, the set of numbers that I can that I should try. And so one tool is my graphing calculator, which I've already set up with this function. You can see here, this is the function we're looking at. And if we graph this, and I've already checked the parameters, if I'm looking about the origin, I have 2 roots here. And I've already checked by zooming out to make sure, because I have to go all the way. If 120 is a possibility and negative 120 is a possibility, I have to zoom all the way out to other ends. I've already done that and then zoom back in. So let's eliminate by looking at the lower bound and the upper bound. So I'm going to come in here and I just want to trace along the x-axis until I get somewhere near my function. So on this side, on the right-hand side, I'm looking at an x value just higher than 6. In fact, 6 might even be an actual root. I'm not positive if 6 is a root, but right around 6 is a root. But certainly none of these positive values above 8. That's nice. I'm getting rid of most of my possibilities. Now let's look on the other side at the lower bound, and I see that I'm looking at negative 6. So I can definitely cross out all of these values greater than plus or minus 6. So I've eliminated a lot of the work, not all of the work, but a lot of the work. And in fact, if I had done this problem on the video, it would have taken a long time, because it turns out that the values I'm going to choose are high values, but I would have gone through positive negative 1, positive negative 2. I would have just gone systematically through the numbers to find the values that I like. And so now let's do a little synthetic division with what I discovered. I have my my coefficients are 1, 1, negative 26, positive 4, and negative 120. And I'm going to use 5. Bring down the 1. 5 times 1 is 5. Add 1 is 6. 5 times 6 is 30. Add negative 26 is a positive 4. 5 times 4 is 30. Add 4 is 34. Hey. Not true. 5 times 4 is 20. Add 4 is 24. And 5 times 24, I know from right here, is 120. And so I get a 0 remainder, so I know that there's a factor of x minus 5 and a 0 of 5. The next one I want to try is negative 6. Negative 6 times 1 is negative 6. Gives me a 0 times negative 6 is 0. Gives me a 4. Negative 6 times 4 is negative 24, leaving a 0 remainder again. So I have, and if I look here, I could keep trying, but look at what I have. I have a constant, I have no linear term, and this is my x squared term, so I'm looking at x squared plus 4, which is definitely not factorable in any way that we know yet to factor. So I can say that f of x can be rewritten as x minus 5 times x plus 6 times x squared plus 4. And this is the instruction I was given, which was to write k of x as a product of linear and irreducible factors, and that's exactly what I have. This is a linear factor, this is a linear factor, and this factor can't be reduced any farther. So it's looking like what I have is the solution type listed here in the second row. I have a positive 0, a negative 0, and now I have to find two complex zeros. A couple ways to do that. One, that always works, is to run this through the quadratic formula. But I think I'm going to use instead the square root property. So I have x squared plus 4 equals 0. So x equals negative 4, x squared equals negative 4. So x equals plus or minus the square root of negative 4. In the past, in Algebra 2, we would sort of at this point to say, oh, no solution, it doesn't happen. And that's only because in Algebra 2 we're dealing just with the real number system. But now we're okay with the complex number system. We want to find all of the solutions or all of the zeros. So we're okay with it, so we're just going to take it and run. And I'll do every step just because it's a quick review. So this is the same thing as plus or minus the square root of 4 times negative 1, which could be broken apart as plus or minus the square root of 4 times the square root of negative 1. And remember, plus or minus, the square root of 4 is 2, you didn't have to remember that, but remember that the square root of negative 1 is the imaginary number or the imaginary element I. So we can now write this polynomial, in this case we have linear factors and irreducible factors, but now we can rewrite it with all of its factors. So we have x minus 5, x plus 6, x plus 2i, and x minus 2i. I have 1, 2, 3, 4 factors. I fully expected 4 factors, and it fits the pattern, one of the patterns I predicted. 1 positive, 1 negative, and 2 complex or imaginary. Now we want to list all the zeros of the function. Well, that's easy enough because each of these, if I set the function equal to 0, will give me one of the zeros. So x minus 5 equals 0 when x equals 5. X plus 6 equals 0 when x equals negative 6. X plus 2i equals 0 when x equals negative 2i. And x minus 2i equals 0 when x equals positive 2i. So I can write it that way. Well, this opens up a new set of possibilities on old work that we've done before. Let's look at, well, first I'm going to rewrite this so I don't have to bump into it later. So in the old days, if I had told you that a polynomial had solutions of x equals negative 3 and positive 7, say, you would have been able to give me the polynomial working backward. You would have said, well, if x is negative 3, then x plus 3 had to equal 0, and x minus 7 had to equal 0 to give me the other 0. Well, that just means, that's just the other side of chicken feet. That means that x plus 3 times x minus 7 equaled 0. And if I distribute, I get x squared minus 7 plus 3 is minus 4x minus 21 equals 0. Done. You've given me the function from the solutions. Now that we have complex numbers in our choices, we can do that with giant polynomials as well. So we want to do an example of one of those. I'm going to tell you that the x values for some function are -3, or the zeros for some function are -3, 1 with a multiplicity of 2, and 4i. And I want you to write a polynomial. Obviously, I'm going to write the polynomial, but this is an instruction that you might receive. Let's break this down. This means that if I have a 0 of -3, then I must have had a factor of +3. And if I had a 0 of 1, then I must have a factor of x -1. But multiplicity of 2 just means it's squared. That's one of those cases where you get the same factor squared, right? And you get a kiss right there on the x-axis. And then I have a complex number, or a imaginary number, a complex number. I have a number, 4i, which means that I had a factor of x minus 4i to get that. But I also know that complex numbers come in conjugate pairs. So I must also have an x plus 4i. So I can already predict a lot of things for this function, right? So this is the factored form of that function. I can say that it's going to end up having a degree of 2, 3, 4, 5. It's going to be a 5th degree polynomial, right? And all I have to do is multiply and expand these out. All right, so you're the student. You're going to be asked to do that, and your job is to be able to practice and be pretty good at it. Although I'm not likely to give you one like this on a test, it is something you should do. But I'm going to use this to sort of advertise a little bit for the kind of calculator I recommend you get. Now remember, I don't actually recommend that you buy a graphing calculator. I think you have enough options available to you that are online or on your phones. But if you buy a calculator, if you want one, I recommend many times, I have said, make sure that it has the letter CAS on it. CAS. And you'll notice mine doesn't. That's because the 89 was the first Texas Instruments calculator that did these functions. Since then, they've produced other calculators that either do or don't do those functions. And so when you buy one, most of you will be getting Inspires, I assume. Make sure you get the Inspire with CAS. CX is not the same thing, CAS. And here's one of the reasons. Notice that I have inserted this group of factors. In fact, if I scroll up and you look at the black line, I've got x plus 3, x minus 1 squared, x minus 4i, and if I move over, x plus 4i. So one of the cool things that the CAS function does is I can go to a catalog, and on the Inspire this is actually much easier to do. I'm just really used to my 89, and so it's the one I use. I can choose to expand this polynomial, go up here, insert it, and the calculator will do the work for me. And the value for you is that when you do this on your own, having a way to check it is really helpful. So if you buy a graphing calculator, you don't need one for my class, but if you're going to get one, make sure you get one that's useful to you as a learner. And one of the ways it's useful is that you can check your work in real time. And so this polynomial expanded is f of x equals x to the 5th plus x to the 4th plus 11x cubed plus 19x squared minus 80x plus 48. It also has a factor tool, so you can see I've loaded in the polynomial that we arrived at, and if I press enter, it'll give me all of the real factors, noticing that x squared plus 16 is just the imaginary factor expanded into the polynomial plane, or expanded into a non-reducible polynomial. And it has a solver, which I've also loaded up in here, that if you set a polynomial equal to 0 and say that you want to solve for whatever variable you want to solve for, it will give you the actual solutions, except notice that it's not going to give me the complex solution. So I have x equals 1 and x equals -3. So it's a useful tool for a learner. Just make sure you get CAS so you have these tools.